Greetings. So welcome to today's class. If we recall, what we did in the previous class was to look at a brief recap of dynamics. We looked at the Newton-Euler formulation and the Euler-Lagrange formulation. So from today's class, we will start looking at vehicle dynamics per se. We will apply whatever we have learned to analyzing the dynamics of road vehicles. Of course, the scope of the course, as I mentioned at the beginning, will be a four-wheeled single unit, two-axle road vehicles. Okay, so that will be the scope of this. So let's start with lateral dynamics. Of course, lateral dynamics is also called as cornering dynamics. Okay, so due to the fact that like we turn a corner, it's also called as cornering dynamics. That's an alternative name given to lateral dynamics. So let's look at where lateral dynamics, what is this lateral dynamics model and where it will find usage before we go into specific models. Okay. So the lateral vehicle dynamic model, right? So as the name indicates, essentially is used for characterizing the lateral response of the vehicle. Okay, by and large in response to a steering input from the driver. Okay, so that's what it is used for. So a lateral vehicle dynamics model characterizes the lateral motion of the vehicle by and large due to a steering input, right? So that's what it is used for. And what it does is that it relates, as we know, as we just briefly recap, when we talk about dynamics, we are going to essentially study the relationship between force and torques and the motion that they create, right? So that's what we are going to study. So a lateral vehicle dynamic model relates the forces, torques that act along the lateral direction of the vehicle lateral direction of the vehicle to its corresponding motion. So what is this lateral direction? The lateral direction is perpendicular to the longitudinal direction of motion of the vehicle on the ground plane, okay, on the road plane. Okay, so that is the lateral direction. So the lateral direction of the vehicle, the forces that are act along the lateral direction of the vehicle to its corresponding motion. Okay, so that's what we are essentially going to be interested in. So in fact, if you look at basic course on vehicle dynamics, by and large, we study, like lateral dynamics, longitudinal dynamics, and all, in isolation or in a decoupled manner, right? But in reality, you will see that there is always going to be coupling, dynamic responses. So what do I mean by that? Suppose when we are turning, anyway, that sometimes we may brake, accelerate, and so on, right? So then there's going to be a coupling between lateral and longitudinal dynamics. And many times when we take a turn, even the dynamics will come into picture, right? So obviously, we are going to deal with coupled phenomena. But then, to begin with, we will study them in a decoupled way. Okay, so that's something we are going to see. Okay, so now looking at it from the perspective of our systems theory viewpoint, where we view entities as systems to which we provide an input and we get an output. So when we look at a vehicle when it's undergoing what is called as a cornering maneuver, so what is the input to the system? The input to the system is going to be the steering input. Okay, so the driver essentially is going to provide an input through the steering wheel, and that is essentially going to result in a response. So there may be multiple outputs. So the rotation of the vehicle about its vertical axis, that is what is called yaw motion, and the corresponding angular displacement is what called as a yaw angle. Okay, so yaw is nothing but the motion of the vehicle about the axis, vertical axis that is perpendicular to the road plane, right? So that is the yaw motion, and the corresponding displacement is the yaw angle. Of course, one may also be interested in what is called as yaw rate. It is the time rate of change of yaw angle. And of course, one may also be interested in lateral acceleration. Okay, so lateral acceleration is the acceleration of the vehicle along the lateral direction, right, as the name indicates. So these are the various output variables one may be interested in. Okay, so yaw angle is also called as heading angle or orientation angle by some, right? So this is also called as heading angle, right? So, okay, so these are this is a visualization of the lateral vehicle dynamics response based on what we have studied dynamic in the perspective of dynamic systems, right? So now the broad question that we are going to ask, right? We are essentially going to deal with lateral motion, right, and even lateral dynamics is the following, right? So the big picture question that we are going to answer is that how does the vehicle respond to a steering input? Okay, so that is the question that we are going to ask ourselves and derive models to answer this. Okay, so but we do that, we are going to look a little bit into the steering mechanism per se and get some insight into it. Then we look at a kinematic model for lateral dynamics before we go to a dynamic model for lateral dynamics. Okay, so that is going to be the progression of our discussion. Okay, as far as this particular module is concerned. Okay, so why we study lateral dynamics amongst others? Of course, we want to essentially characterize or understand the cornering response of the vehicle. Okay, studying lateral dynamics is extremely important when we want to do objective evaluation of handling response. Okay, so what are the applications? Okay, so that's what I'm listing down. So when we want to do objective, so-called objective evaluation of handling response, okay, so a lateral vehicle dynamic model becomes very important. In fact, we will learn something called as a Memoro plot, which can be used for doing an objective analysis of cornering or handling response. Okay, and of course it can be used for various control applications. Okay, so we will learn one of them when we go for case studies and automotive controls course. So we will with now increasing penetration of autonomous vehicle, right? So even the yaw angle control or heading angle control, which is very important if you want to essentially have a vehicle autonomously follow a trajectory, right? That becomes very important. If you want to do yaw stability control, right? So, or what is called as directional stability control, right? So, which are part of electronic stability control systems. It becomes very important for studying the lateral dynamics. And even when we want to essentially predict the vehicle response for applications such as lane departure warning or lane keeping and so on, understanding the lateral dynamic response of the vehicle becomes useful. Okay, so that's where we are going to use some of the models that we are going to stick. All right. Okay. So this is a brief preamble to lateral dynamics. So the first topic that we are going to study in lateral dynamics is about the steering geometry. So there are various methods by which a vehicle can be steered. Most road vehicles are based on the concept of so-called Ackermann steering geometry. Okay, so that's the first concept that we are going to learn as far as lateral dynamics is concerned. Okay, so what is Ackermann steering geometry? So let me explain it using a simple schematic. Okay, 1 minute. So let's consider a very simple schematic of a four-wheel vehicle, right? That is being turned, and essentially we consider. Sorry. Yeah. Okay. So we essentially are going to consider this four-wheel vehicle, okay, and we can observe that like. Points A and B are the centers of the two front wheels, okay, where they contact the tire. And these are we assume front wheel steering, okay. And these are the two wheels that are being steered. And without loss of generality, like we are drawing this diagram by looking at the vehicle from the top. And let's say that the vehicle is steered to the left, okay, like when we look at it from this view, okay. So here, L, the parameter L, which is the distance between the front wheel center and the rear wheel center, is what is called as the wheelbase of the. Okay, so as we can observe, okay, so this parameter L, capital L, is what is called as the wheelbase of the center. And as we know, the vehicle's center of gravity is indicated by CG. Okay, and we assume that the vehicle CG is at a distance of L1 from the front wheel center along the longitudinal axis of the vehicle, and at a distance of L2, like from the rear wheel center along the longitudinal axis of the vehicle. Okay, so those are the two important parameters that characterize the longitudinal location of the center of gravity. Okay, so consequently, L1 plus L2 is going to be equal to capital L. Okay, so A and B are the what to say points of the two front wheels. Okay, the inner wheel and the outer wheel, respectively. And W is what is called as the track of the vehicle. Okay, so which is the distance between the two center points, right? So on the front wheels. Okay, so that's what it is, right? So this is what is called as the track of the. Okay, so right now we assume that the track is the same for the front and the rear, just for simplicity to begin our discussions. Okay, all right. So now, of course, C and D indicate the center points of the rear wheels, where they contact the road interface, right? So that's what C and D indicate. Okay, so delta I and delta naught are the steering angles of the inner and the outer wheels. Okay, so delta I and delta naught indicate the steering angle inputs, okay, at the inner and the outer wheels respectively. Okay, so these are the steering angle input at the inner front wheel and the outer front wheel. Okay, so obviously we assume front wheel steering and the outer front wheel. So we assume front wheel steering, the rear wheels are not steering. Okay, so what is this Ackermann steering? So the steering geometry is designed in such a way that when the line, like line segment which joins the points A, okay, to the center point of the rear axle, okay, and let me draw this line. Okay, so let's say the steering geometry is designed in such a way that, like when we project the links of the steering mechanism, the lines joining, like the line segments joining the points A and E, right? And the line segment joining the points B and E coincided or intersected. So, okay. So that is a primary idea. So we designed the steering mechanism such that when the links of the steering mechanism are projected, when the vehicle is in the centered position, right? When we project them, the extension of those links will meet at the center of the rear axle. Okay, so that is the basic idea. And the another way to visualize this is the following. That is, if we draw, line segments that are perpendicular to the two wheel planes. Okay, so we see that there is a central wheel plane of the front wheel. We draw a line which is perpendicular to it, and there is another line which is perpendicular to the outer central wheel plane of the outer wheel, and we project them. They intersect at this point O, which is on the rear axle, the center line of the rear axle extended into the turn. Okay, so this is another way of visualizing this steering geometry. And this point O is what is called as the instantaneous center of turn. Okay, so let me repeat that. Another way of visualizing this Ackermann steering geometry is that if we draw the lines perpendicular to the two front, to the central planes of the two front wheels when they are turned by delta I and delta naught respectively, that the two lines intersect at a common point O, which is on the line which is an extension of the rear axle center line, okay, CD. Okay, so that is another way to visualize this. So consequently, what happens is that these angles, okay, like this once again simple geometry, using included angles between sets of perpendicular lines. This angle then becomes delta I because this angle is going to be between two lines which are perpendicular to the central wheel plane and the horizontal on the longitudinal axis. So this is going to be delta I, and similarly, this angle is going to be delta O. Okay, so this is pretty straightforward, right? So I'm sure all of us are, how to say, exposed or are familiar with, basic geometry, right? So that essentially tells us that the included angle between two sets of perpendicular lines, right, would be the same. Okay, so now when we draw the line segment from the instantaneous center O to the center of gravity, the length of that line segment is R, okay, and R is the turning radius. Okay, so the parameter R is the turning radius. Okay, and let's call the distance from O to E as R1. Okay, so this is a parameter which we are introducing just for the sake of simplicity. But when we derive the equations, we will be eliminating them. All right. So that's where we are. That's why we are introducing this parameter R1. Okay. Now, just to mark a few more parameters that will help us derive some expressions. This distance is going to be equal to W by 2. Okay, so we assume the front track and the rear track to be the same. Sometimes they may be different, but then like in this derivation, we assume them to be almost the same. And then this distance CE becomes equal to W by 2. Okay, so that is something which is once again understandable. All right. Okay. So this is the diagram associated with the Ackermann steering geometry. Okay. So before we go ahead, any questions on this?
Sir, why we've assumed angles to be different for the front wheels?
Okay. Why? Okay. So that's because when we take a turn, right, the inner wheels have to be rotated by a larger angle, or the inner wheel needs to travel on an arc of smaller radius than the outer wheels. Okay. That is why we rotate the inner wheel by delta I, and outer wheel by delta naught, and delta is greater than delta naught. Okay, so we are not calling it left and right. I'm calling it inner and outer, because if you change the direction of rotation, now the right wheel will become the inner wheel, the left wheel will become the outer wheel, right? Is it not? Okay, yeah.
Okay, got it, sir.
Yeah.
Sir, can you once again explain the projection of that to the point E? Like I was not
Okay.
able to understand clearly.
So the way this mechanism was visualized is the following, right? So suppose I will draw a trapezoidal mechanism. We are going to learn about the trapezoidal mechanism in the next class. Let's say this is the line segment AB. Okay. So the way this Ackermann steering geometry was postulated is that, let's say we have a four-link trapezoidal mechanism, okay, steering mechanism like this. So this is the shape of the mechanism when the wheels are centered. Okay, there is no steering. All right. So the way it was visualized is that, like, if we project these links, right, they essentially intersect at point. Okay, and how the Ackermann steering geometry was initially visualized and developed.
Okay.
Yeah.
So,
Please
if
go
the
ahead.
wheel base is increasing, sir, then essentially the distance between the two wheels should also increase in order to have this mechanism working.
Then you may need to adjust the steering mechanism itself, right? So if you have constraints on the track, we are going to derive equations. Okay, yeah.
Okay.
And I will give you an optional assignment where you will do coding and see what to say. We can get a feel for ourselves. Okay, so I think both questions are very I think important. In fact, I should have explained that delta I delta naught difference. Thanks for raising it. And even this question is very important. Okay, so we are going to learn about the trapezoidal steering mechanism in the next class. Okay, but this is how Ackermann postulated it. Okay.
Okay, sir. Thank you.
Okay. Any other questions before we go ahead and derive the equations?
Sir, is it a requirement that point E should always lie on the center of CD line?
No, that's how it's postulated. Like not necessary. So, in fact, we will see that whatever Ackermann steering condition that we are going to derive will not be satisfied at all steering positions. Okay, yeah. This is only an ideal requirement. Okay,
sir.
This is once again a postulation. Okay, yeah.
Hello, sir.
Please go ahead.
Sir, there are a few models with the steering system on the rear axle, right, sir? Like a forklift
Yes.
or something.
Correct.
Yes, will there be a mirror image of this one?
Okay, very good. Okay, so what happens when we have rear wheel steering? Okay, and in fact there are cases where we may have all wheel steering also, right? To essentially have a tighter turning radius, right? Is it not? If you have pure rear wheel steering, it's similar geometry. You once again the idea is to essentially go for a similar arrangement. Okay, if you have four-wheel steering, what will happen is that, like, the point O, okay, I'm just marking it somewhere here, depending on how I will erase this later, just because this question came. If you have four-wheel steering, even the rear wheel will be steered like this, right? So, and we essentially take the perpendicular lines. Okay, this is not a great diagram, but then so what will happen is that, like, we may need to adjust the angle such that the point O comes somewhere here. Okay, so the angles have to be adjusted so that, like, the point. Okay, so you can see that immediately the turning radius becomes smaller. Okay, yeah, with all wheels steering. All right. Any further questions? Okay, so let me erase this thing. Okay, so because I don't want to. That. Okay, great. Okay. So, if there are no further questions, let's go on, right? So this is the setup. Of course, and where where do all these things fit in? Like if we take a macroscopic view and figure out where these things fit in. In fact, like we were looking at lateral dynamics model, right? So we are interested in characterizing the vehicle's lateral dynamics, right? So when we want to derive the lateral dynamic model, I told you that the steering angles are the inputs, right? So we will have this delta I, delta naught going as inputs to the system, and we may have various outputs, right? The yaw angle, the yaw rate, the lateral acceleration, and so on, right? Psi is the yaw angle. Okay, so yaw angle is denoted by psi, yaw rate is denoted by psi dot, lateral acceleration is denoted by A subscript Y. Okay, so those are the symbols I am using here. So you can see that those are the outputs. However, if we essentially go from the steering system to the lateral dynamic model, see, by and large, what will happen is that like we may have the steering angle input given by the driver, okay, or the steering wheel to give this what to say angles of the steered wheels, okay, delta I and delta naught are the angular displacements of the steered wheels, okay. So this theta driver, what I'm indicating here, will be the steering angle input provided by the driver, right? Whereas delta I and delta naught are the angular displacements of the steered wheels, okay? So there's a subtle difference between them, right? So we need to essentially have a model for the steering system to essentially go from theta driver to delta I, delta naught. Our focus will be on this, okay? In this particular course, we are going to look at lateral dynamic model. There are models for the steering system, right, which can essentially relate the steering angle displacement to delta I delta. Okay, so that's something which are those models are available. Like we are only going to discuss this lateral dynamic model. Okay, so that's what we are going to focus on in this particular course. Okay, so I just wanted to tell you the overall flow of information as far as modeling the complete cornering responses. Okay, fine. Going forward, let's derive an equation that will help us in relating various variables associated with the Ackermann steering geometry. Okay, so let us consider triangle OAC. So let me go up. So what is this triangle OAC? It is this triangle, right? OAC. Okay, so that's what we are. So if I consider, let's say I draw a line from A to C, so that like things are clear. So we are going to consider triangle OAC. So if we consider triangle OAC, immediately we can see that this angle, okay, angle AOC is delta I. So immediately I can write tan delta I to be AC by OC. AC is the wheelbase L, and what is OC? What do you think will be OC in terms of, let's say, other variables indicated in this figure?
R1 minus W by 2.
Very good. R1 minus W by 2, right? Consider triangle OAC. Consequently, tan of delta I will be equal to AC divided by OC. All of us can agree that this length of this line segment AC is capital L. Here, the wheelbase. OC is going to be this length, but OC I can OE minus C, right? And OE is capital R1, E is W by 2. Okay, so consequently, OC, right? This is OC. OC is going to be equal to R1 minus W by 2. Okay, so let's write it. So this is going to be L divided by R1 minus W by. So this implies that cot delta I, I'm just going to invert this ratio. Cot delta I will become R1 minus W by 2 divided by L. Okay, so let's call this as equation number 1. Okay, so I hope it's clear how we got this. Okay, so I hope it's clear how we wrote down this equation for triangle OAC. We are going to do something similar with triangle OBD. Okay, so let's now consider triangle B. Okay, so if I consider triangle OBD, so O is once again here, point B is here, and D is here, right? So let's say I draw the line segment from B to D. Okay. Now, what will happen? Like I need to essentially look at angle BOD. Okay. Angle BOD is delta naught. Okay. And tan of delta naught is going to be BD by OD. And immediately OD we can easily write down similarly saying that it's going to be OE plus E. And that's going to be equal to R1 plus W by 2. Right? I'm sure all of us can agree to that point. Right? So let's write that. Okay, so tan delta naught, okay, is going to be equal to BD by OD, okay, which is going to be equal to L divided by R1 plus W by 2, okay, which implies that cot of delta naught become equal to R1 plus W by 2 divided by L. Okay, so let's call this as equation number. Okay, so we have derived two equations, right? So from the two triangles, okay, OAC and OB. Now we subtract equations 2 and 1. So from 2, let us say we subtract 1. Okay, so let us say we do 2 minus 1, right? What are we going to get? If we do 2 minus 1, we are going to get cot of delta naught minus cot of delta I. That's going to be equal to R1 plus W by 2 divided by L, okay, minus R1 minus W by 2 divided by L. Okay, so if we simplify this, what are we going to get? We are going to get W by L. Okay, so R1 will cancel off, W by 2 and minus of minus W by 2 will become plus W by 2. So they will add to give us. So this becomes a very important expression, which is cot delta naught minus cot delta I is going to be equal to W divided by. Okay, so this is a very important relation that gives us an equation that to relate the track of the vehicle, the wheelbase of the vehicle with delta I and delta naught. Okay, so that we get something which we just discussed. Okay, we get displacement of the steering system according to the diagram that we have drawn. Okay, and this condition is what is called as the Ackermann steering condition. All right. So we can immediately see, like as one of our friends asked, right? Let's say if I increase the wheelbase, right? What is going to happen? Obviously, the difference, and if I keep W the same, the difference between cot delta naught and cot delta I will decrease, right? So when I turn my inner wheel, automatically the angle by which I turn my outer wheel should be changed, right? To essentially take into account the increase in the wheel base, okay? To meet this Ackermann steering condition. However, it so turns out that, like we won't be able to meet it all the time. Like we will see when we look at construction of the actual mechanism, we will essentially see how, at what conditions this steering Ackermann steering condition would be satisfied. Okay, so we will see that it's not going to be satisfied all the time. It's going to be satisfied at a specific position. Okay, so we'll look at it as we go along in our discussion. Now, having derived this Ackermann steering condition, now let us add equations 1 and 2. Okay, so let's do that. Okay, so if I add equation 1 and 2, what is going to happen? If I add equations 1 and 2, I will get cot of delta I plus cot of delta naught. It's going to be equal to R1 plus W by 2 divided by L plus R1 minus W by 2 divided by, okay, and this will become, as we now can see that plus R plus W by 2 and minus W by 2 will get cancelled. This will become 2R1. Okay, so this, if we simplify, we can get an expression for R1. So what is this expression for R1? We will get an expression for R1 as L times cot delta I plus cot delta naught, okay, divided by 2. Okay, so this is an expression for R1. Okay, so why do we use this? We are now going to use this expression for R1 to derive an expression for the turning radius R. So now let's go back. Okay, so I want to essentially derive an expression for the turning radius. So what we are going to do is that, like, we are going to consider this right triangle O CGE, right? If I consider the right triangle OCGE, I use the Pythagoras theorem, right? So this is R, this is R1, and what is this distance? This is L2. So what is the Pythagoras theorem relationship here? We know from Pythagoras theorem that the square of the hypotenuse is going to be the square of the two perpendicular sides, right? So R squared is going to be R1 squared plus L2 squared. Okay, I'm sure all of us can immediately understand that, right? Is it not? Okay, so I'm just going to use that relation. Okay, so now the turning radius R consequently will be square root of, okay, square root of, okay, L2 square plus R1 square. Okay, and then we essentially are going to substitute this expression for R1. So this is going to be L2 square plus L square times cot of delta I plus cot of delta naught whole square divided by 4. Okay, so this is what we will have for the as the expression for the turning radius. Okay, which is expressed in terms of these parameters, various parameters. Okay, so I hope this is clear. Okay, so how we got it. Okay, so any questions on how we got the Ackermann steering condition and an expression for the turning radius? Okay. So in fact, now I'm going to discuss something which I feel is very important and which I think we need to put in some thought, and also I'm going to leave a part of this question as the second portion of your homework number 4. So if you recall, one part of homework number 4 was given yesterday, right? So where I requested you to derive the equation of motion for the mass spring damper system using both the Newton-Euler and the Euler-Lagrange formulation. Okay, so we are going to look at another aspect of Another problem related to your homework number 4, right? So the question I'm posing to you is it like how do we determine the CG of the vehicle? So we can see that like in most of our discussions, like these parameters L1, L2, some people will call it LF, LR, some people will call it AB, and so on. Okay, so depending on the textbook or the reference, you will have L1, L2 as the indicating the longitudinal distance of the CG from the front wheel center and the rear wheel center. Some textbooks or some reference will use LFLR, okay, to indicate these distances. Some textbooks will use AB, okay. So these are equivalent symbols used to refer to the same thing. Ultimately, what it means is that L1 plus L2 will be wheelbase, LF plus LR will be wheelbase, A plus B will be equal to the wheelbase, right? The question is, like how do we determine the values of these parameters and also the height of the CG? Okay, so that is also important. Okay, so now one way, to determine the values of this L1, L2, like I'm just drawing a very simple schematic just to convey the concept. Let us say I have a stationary vehicle, right? And let us say, like I consider this to be a car, okay? And okay, I think I drew the other way around. 1 minute, sorry. Okay, so let's say this is the front of the car, okay, and this distance is going to be equal to the wheelbase L. Okay, and let us say the CG of the car is somewhere here, and we want to look at the location of the center of gravity. So what do we do? So at the CG, we know that the weight of the vehicle is going to be concentrated. Let's say we call that as W. And let's say the normal force at the front wheel we call as WF. And then the normal force at the rear wheel we call as some WR. Okay. And this distance between the front wheel center and the CG is L1. Okay. And this distance between the rear wheel center and the CG is L2. Okay. These are things which we already know. And the vertical distance from the ground to the location of the CG is the height, CG height H. Okay. So suppose, like how can one get L1 and L2? Suppose, let us say I have this vehicle parked on a flat surface, right? It is stationary. And I put in some weighing scales to measure WF and WR. Then what I can do is that, like, I know that WF plus WR is going to be equal to W, okay? And let's say, we call this front wheel contact point as A, rear wheel contact point as B. And let's say summation of the moments about point A equals 0 will give me WR times capital L minus W times L1 will be equal to 0. Okay, so that's what I would have, right? So if you take moments of the various, there are only 3 forces, right? So WF, WR, and W. When I take moments about point A, the moment of WF vanishes, right? So I get WR times L, capital L, minus W times L1 will be equal to 0, right? So this implies that L1 will become W. So if you simplify this, L1 will become equal to WR by W. I'm writing it carefully, times L. Okay, so we can get this, right? We know the wheelbase, able to measure WR, we get L1, right? Similarly, if we take the moment about point B and equate it to 0, we will have WF times L minus W times L2 will be equal to 0. Okay, just a similar process. So we will have L2 to be equal to WF by W times capital. Okay, so we can immediately find L1 and L2. The moment we measure WR and WF, we can find L1 and L2. Okay, so this is a very simple technique to get L1 and L2, right? Is it not? Okay, and we can immediately observe that, like if we have a typical passenger car where more load front, right, more static load is on the front, then obviously WF is going to be higher, so L2 is going to be larger. That means the CG is going to be towards the front, right? On the other hand, if you have more static load on the rear, like let's say a truck or a lorry, right, then L1 WR is going to be higher, then L1 is going to be larger, so the CG is going to move towards the rear, right? So I think it's very intuitive, right, from these expressions. And even we can rewrite the same expressions to get the static load distribution. So the static load on the front wheel will be WL2 by L, and the static load on the rear wheel will be WL1 by L, right? So this indicates the static load distribution. Okay, so we have got a very simple method to find L1 and L2, right? So what I want you to think through and answer as the second part of homework is that, like, how do we get the value of H, okay, which is the height of the seat. Okay, so please explore methods that will help us in getting the value of the height of the center of gravity. And I want you to explain that method and also derive equations using simple diagrams like this and show an expression for them. Okay, that's what I want you to do as the second part of homework number 4. Is it clear what I'm expecting? Any questions about this?
Sir, question, how to determine the CG of the vehicle? Already you mentioned it, so already you explained it, right? Do we need to again give some explanation?
So I only see the CG of the vehicle. We need to get L1, L2, H. I only explained how to get L1 and L2. Yeah.
Okay.
So yeah, that you don't need to write. Okay, I am only asking you, how do we get H, right? So
yeah.
I hope I have clarified, right? So
yeah, yes.
So this is your second problem of homework number 4. So please think through. You can look up books, online resources. What I want you to do is, like, I want you to explain very clearly what is the process that you will follow, right? And draw some free body diagrams, and then schematics, and then get expressions that will ultimately give me a formula for H, just like what we derived for L1 and L2, right? So we derived these two equations for L1 and L2, right? Is it not? Similarly, some equation for H based on an experiment that you will propose. Okay, so that's problem number 2 of homework. Is it clear? All right. So are there any questions based on what we discussed today? Right. If not, let me stop recording.